Okay, looks like we're rolling. And welcome everyone to Solver Madness. I am super thrilled to have you here, Andrew, today. And I am actually going to hand it over to you to introduce yourself and let's get started.
All right. Yeah, welcome everyone. Thanks for joining us. My name's Andrew Weiler. I've been working at this for maybe 20 years now, mostly in the VFX world. I got my start doing that, and found myself gravitating a lot toward dynamics at the time in Maya. And then about 5 years ago, I realized all the things that were very difficult to do in Maya required a lot of scripting, a lot of Mel, a lot of Python, were actually crazy fast to do in Houdini. I have not looked back. And the more I've gotten into doing Houdini, the more I've been specializing in those kind of effects, visual effects, and quite a lot that kind of goes over into the world of motion design. So they tend to kind of inform each other. I find myself a lot of times doing things that's kind of in both fields. So bringing kind of a VFX approach to doing more design projects and vice versa has been kind of an area that I dig deep into, if that makes sense. So this effect, I think, is really fun in terms of looking at it from the standpoint of a production session. But really, the way I want to approach it is how can we use these kind of techniques of layering and combining a lot of different simulations into building pretty much any effect, from really realistic ones to more stylized and designy kind of things. And so I think it's more about digging into some interesting principles that we can apply to many different things. And that's kind of how the course is structured. I'm starting with this kind of effervescent bubbling effect that happens that transforms this martini glass into bubbles.
Are you, you're not sharing your screen. I'm not sure if you're
Oh,
meaning to.
I'm sorry.
It's
Yeah,
okay. Just
let me
making
go ahead
sure.
and do that. Yeah. Actually, at this stage, we can totally. So let's see. Yeah, are we good?
Looks good here.
Yeah, perfect. We'll start with building the martini glass, which I don't have a slide for at the moment, and end with the one that you see here, which is kind of gonna be a way to apply the concepts that we learn to something that's a little bit more abstract. It's almost like it's the reverse. So in the first two sessions, we'll bubbleize our martini glass, and in the last session, we'll take those concepts and actually build a shape with our bubble simulation. That makes sense. Yeah.
Yep, you're good.
Okay. Shall I dive in?
Let's do it.
Okay. So, Solver Madness. That was the title we came up with, which is fun, and I promise it won't get too mad. But we'll dig into some fun concepts. And first of all, since it's called Solver Madness, we should just talk real quickly about what is a solver. And Wikipedia gives us this definition: a piece of mathematical software that solves a mathematical problem. A solver takes a problem, it takes problem descriptions in some form of generic form and calculates their solution. I kind of came up with a more concise definition, and I think in Houdini speak, basically a solver is the math and or data process that happens at every time step of a simulation. So just to get that out of the way, we can move on. This is some reference, and we can talk a little bit about the effect that we're building. Let me get some notation here. So what we're going to do is, let's break this down a little bit. And it's not exactly like this, and the way we're approaching it may be a little bit more stylized. But this, we can at least kind of go over the main elements that we're building, starting with our main bubbles. And then those bubbles are spawning secondary trail bubbles. And then there are a lot of kind of mid-range, mid-scale bubbles. The thing that we don't have in these images is the flip source. We're actually going to have kind of like, a core of actual liquid flip that everything spawns from. So from that flip, we have bubbles spawning off of it and taking velocities, as you can see by my awesome art. So we have primary bubbles, we have secondary trail bubbles, we have mid-scale and smaller foam bubbles, these tiny little ones. And then an element that we don't see in these images also is we're going to set some rules to burst these bubbles at different stages, and then they'll kind of spawn secondary bubbles again. Does that make sense? So that gives us kind of the main elements of the effect that we're building. And we're going to do this kind of manual. We're going to approach this not by doing anything fancy with flip tanks or air pressure or anything like that. We're going to kind of simulate these bubbles moving through a watery medium. And we're going to do that with pyro advection. So running the pyro advection, adding the velocity of the pyro to the motion of our particles will give us that kind of watery, swirly effect. And that's pretty much the concept of what we're doing. Let me see. One second here. I'm trying to get out of this mode here. There we go. All right. So, and since we're all Houdini users and we love colored tiles connected by lines, we put together this little flow chart. And we'll just go over this real quickly. So starting from our source geometry, which in our case is going to be the martini glass, that gets fed into a growth solver, which is going to be kind of the core that we'll go over today. And from this growth solver, we can derive all the sourcing for the downstream sims. So volume source for pyrosim and point sources for pop sims as well. This also, when we run the solver, we're going to use that to dissolve away the geometry that we no longer need to give us a smooth transition between the martini glass and our effect. Downstream from that, we have pyrosim, and you can see this gets fed into all the simulations. So we have an advection line that goes into each one. And we're using slightly different advection settings for each simulation to, when they combine, to give a lot of overlapping complexity. And we'll dig into that. So next, you can see from the flip sim here, that also becomes the source for trailing bubbles from that that flip sim. And the main bubbles are feeding into another simulation that creates trailing bubbles. Along with bursting, it's creating secondary burst bubbles. So next stage is these all go into a process here where we can set a threshold to say what is going to be rendered as point primitives and what can we mesh together and render as a mesh. And that's pretty critical because we're going to have quite a lot of particles, and a lot of that finer detail, foamy detail, comes from rendering them as points. And then we can just kind of set the threshold that we want, a p-scale threshold, basically. One thing I'm missing here also is that the flip sim does actually feed into this VDB mesh. So everything goes through here, and then we have two outputs at the end, meshes to render and points to render. So does that all make sense? Anything before we move on? Okay.
Cool. And you guys can type your questions in the chat if you feel comfortable. I think everyone's good though.
Okay.
Go for it.
Let's dive in. Okay. So just a couple things to get started. We'll come back to caching towards the end when we talk about PDG and caching. But if you want to run caches on the file that you have, you can go to the aliases and variables, and everything is relative to this variable called cache. So change this to your local drive and you can run any of the caches if you desire. No need to if you don't want to. And the only caches that you need at the moment are going to be the first couple ones. If you go into this top net here, it would be these right here, source cache. So with that out of the way, let's dive in. All right, so we're going to start in this geometry container called growth source. This is going to give us the foundation for our effect. Let's see. So the output of this gives us two things. Number one, we have points to source. Let me turn on lit spheres. So point sources, and if I template these points will give us a source for everything downstream, all the sims, pyro, flip, and particles. And at the same time, we're outputting the martini glass. We're dissolving it away. That's, you can see here. And if we overlay those two together, you can kind of see this will give us a smooth transition where the red particles are the source for all of our simulations. And then you can see it dissolving away. It all matches up. And that gives us the really nice, smoothly transitioning effect. And we're going to show how that's done, how that's built. So far, so good. So
Actually, one question here. Which cache should they run first? Let's say if they're trying to follow along.
Well, we'll cover this too, because sequence is very important. But if you actually just cook this right here, the bottommost PDG node, go cook node, that will cook these two. And those are the only caches.
And so what they need to do is make sure they in the global settings that you just showed, like make sure to set it to the right place on their hard drive.
Absolutely.
And then all they have to do is that.
And that's all they have to do.
Is that, you have that, Philip? Is that cool? Okay, hopefully we're good. Go for it.
So let's talk about growth solvers. And I'm sure a lot of you folks have worked with them. It's kind of a core concept in Houdini, but probably bears talking about a little bit. So in the simplest terms, actually I have a little explainer over here. In the simplest terms, a growth solver is, you can, you give it a starting position. It's an algorithm that creates smoothly growing attributes across geometry or points. It propagates what you give it. So it loop over the points from a start position and then propagate those values throughout. And you can see this little sphere right here is actually sized to the radius of what we're searching from. And that'll make more sense a little bit later on. So you can kind of see just in abstract what's happening here. In fact, let's talk about this pyro source spread real quick, because that's a good example of a built-in growth solver that comes with Houdini. So pyro source spread is really a purpose-built growth solver, and that you set a temperature. I might have to reset my viewport here. You set a temperature value. I don't know why it's not visualizing. Here we go. So you grouped some start points here. In this case, we're just using a couple lines of Vex to set the temperature to 1. In the pyro source spread, it takes those temperature values and then starts propagating them throughout the point cloud, and you can visualize it here. And that is purpose-built to spread attributes that you would need to do pyro, spreading fire in a pyro. If I blast away anything that's any of the points that are at a burn value less than 0, you can just see how that kind of gets rid of everything. So that's an example of a growth solver, but we're going to do, and if we dive in, actually, let's dive into that real quick. You can see inside here, it's just a package solver. So essentially, purpose-built, we're just going to be doing this from scratch in essence. All right. So let's see. So this particular solver is point-based. There's also a lot of different ones out there that use more like mesh-based. They'll go along the surface of a mesh, but this one's great for more dimensional effects. And it's based on a point-based implementation that the brilliant folks at Intagma presented, I think at FMX a few years ago. And I've added a few things to it, which we'll go over. And the main thing is I've added some noise weighting so that we can get this sort of crinkling. We can get this sort of crinkly edge here. So there's noise added so that the leading edge has some more interest to it. I'm also calculating vectors in the general direction of the growth, which we can use to source velocity. And I'm outputting a variable called my age, which is basically a timestamp at every point. And what we want to do, what we're going to go over here, is a way to build this so that we only have to run the sim once. So someone once said, sometimes the best sims are the ones you don't have to run. So we don't want to have to run the sim every time we build this growth effect. You know, we don't want that to be dependent on any downstream sims. It'll be a lot faster and easier if we can just run it once. Then we'll get a timestamp on all of our points. And then downstream from that, I'm going to show you how to build a simple setup with some Vex expressions that we can just kind of animate with keyframes almost in real time. So far, so good?
Yep.
All right, let's step through how this is being built. So first of all, we have our glass object, and we're just doing a points from volume to get a point cloud. We're going to group a few points. This is going to be our starting point for the growth solve. And on that start group, we're setting a few attributes. Well, one attribute and a group. We're setting an attribute called infect to 1, and we're putting it in a group called infected. This right here is just shorthand in Vex to say, make a group called infected and add the points to it. So anything in that start group here, which is just a bounding sphere, will be added to that group called infected. And then another branch here is doing the inverse as far as the infection. We're setting the infect to 0 and creating a different group called food. So we merge those together, then layering 2 noise, attribute noise SOPs. And the first one here is just multiplying, and the second one is adding. And that just gives us something we can use later on to weight the growth pattern, give us some more interest. In this attribute wrangle here, we're taking the X component of that noise. We only need it as a float, and storing it in an attribute called add noise that we can use later. And after that, we can just set the color value to 0 so it's not distracting. So that takes us to the first solver that we'll be talking about in this course, appropriately named the solver SOP. So I'm going to go over this a little bit more in broad strokes as far as how this is built, and then I'll go back through and talk about it more line by line. But let's talk first about what the solver SOP is. So let's see, let me look at my notes real quick. So a solver SOP is basically a DOPNet. It's a DOPNet that's been packaged to work with SOPs. And the clue here is in the switch operator that we have. You can see I have an expression on this switch. I'm referencing up here, I'm referencing the start frame for this solver so that at the beginning, we're looking at the first input. And after that, it switches to the previous frame. And that's the way a solver SOP works. You're always working on the previous frame, doing stuff to it, and that feeds back into the next frame. So you're able to loop over SOP geometry coming in from the first input, actually working on the last frame. And that's important to remember. And then you can use any SOP operations on that. It loops back through again. So in essence, you're able to create something with SOPs and two SOPs at every time step. All right, so let's see. Let's dig into this. Everyone with me so far?
Yep. So we
Okay.
have a question. So the switch is because on the first frame, there is no previous frame.
Exactly right. Since we're always working on the previous frame, on the first frame of our simulation here, we want to take the live input. And then after that, we can switch it.
Great.
Okay. All right. So here's the guts of the growth solver. And I promise this will be the most math we dig into in this course. But since we're dealing with some interesting concepts and using near point function, which is very powerful, especially inside of SOP solvers and solver SOPs, we might as well dig into it pretty deep. And what I'll do is I'll go over this whole process first, and then we'll go over it line by line and talk about what it's doing. So let's go over here to a little explainer we put together. If you go over to this in this area called demo and open solver, you see I have this growth solver explainer, and I've set this up in a way that you can experiment a little bit on your own with this and see what it does. If you're like me, seeing the output, the outcome visually of something like this is super helpful. And I'm going to, well, I better pin this screen and get into the solver here. All right, so first off, I'm going to do this just in 2 dimensions. So just bear in mind that this is actually working in 3 dimensions on a point cloud, but it's going to be much easier for us to look at this one point at a time. So I have a few points just to illustrate our point cloud. And the white ones are the infected ones. The black ones are going to be food. So we have one infected point at the moment. And I'm going to kind of describe this process. So starting with the first line here where we're setting a radius. And that's going to be the search radius that we'll use in a moment with near points. So next, we're creating an integer variable called NBRS. And these little square braces indicate that it's an array. Array is just a way to store a list of values. So where other variables might just store a set amount of values, an array can change based on how many values we're storing in that array, if that makes sense. And what we're storing in that array is the results of the near points function. So what the near points function does is it takes input, in this case, a point, or in this case, a group, and searches nearby points based on a radius that we set, and stores a value that you can also set. In this case, it's the position. So what this is doing is it's saying for infected points, search neighboring points inside this radius, which I'm specifying with this circle, and store a list of their positions in this array called NBRS. Now, next, we're going to set a few variables because we want to loop over that array at every frame. We want to take what was found in this radius and do some stuff with it. So we create an integer called CNT, which is for count. We'll need that because we want to know how many times we're looping over those points. Then we create a float called accum, where we can accumulate values, and then a vector called dir, which we'll use to find the direction from our infected point to the closest one. So far, so good. So I'll come back to this loop. We're going to loop through all those. I'll come back to this in a minute and go over it line by line, but let's skip forward just to get the basic concept. What this does is it accumulates values at every time step. And then it stores that in an attribute called infect. So you can see it's adding that accumulated value there. And it's also taking that count that we created, which is how many times did this loop? Essentially, that's how many points is it processing at every step, and then divides it by that, so we can get a number that's an average of all their positions. Along with that, I'm taking the direction vector, which we'll come back to in a minute, and creating a vector that's in the general direction of growth. So let's just go to the next wrangle here. What that does is once a point is infected, in fact, we can step forward. So this point now infected this point. Once that's infected, if the infect attribute is greater than 1, then you add it to the group called infected and take it out of the food group. So now this point is no longer food. The infected points won't have to search for that. That's an important optimization. And you'll see here in the algorithm for growth, it's only operating on points that are in the food group. So in this next one, it takes it out of the food group and it's infected. And at the last stage here, once it's added to that infected group, start incrementing an attribute called my age. And this is the main output that we need, because essentially that gives us a timestamp at for every point. And then we don't have to run the simulation anymore. And we'll talk a little bit more about that. So stepping forward here, let me make sure I'm visualizing the right attribute here. Yes. So in fact, you can see here, this point here is searching for points inside of its radius. And you can see it's already at a value greater than 1. These ones are incrementing forward. And you can see at the moment, this one exceeds 1. It's now part of the infected group. It has its own search radius. It's looking for nearby points. Those are incrementing. And then on and on and on. And that's how you get that kind of smooth growth. And the reason growth solvers are so handy is because they give a very natural output, something that mimics nature. So think like spreading mold, or the way roots grow, or the way cells are infected. And here's an interesting thing. Look at this point down here at the bottom. It's taking a long time to get infected because it's at the very limit of the radius of the growth solve. So as we step forward, you can see it is incrementing forward, but slower than the rest. And that's an important thing because we're going to get into weighting. Now, if we just said search for surrounding points and add them to the infected group, all these points would instantly be added to the infection growth. And then we would just get a big clump of points. And then in the next time step, another clump of points. So weighting is a very important step in this process. And let's talk about how that's done. That's kind of getting into the guts of this algorithm. All right, so let's do this line by line. Let's talk about how this is going. So anything before we actually dive? We're going to dive deep into this one. So any questions or anything?
One question. So so where a point is inside of the radius decides the order of infection.
That is correct. Yes. In fact, that's exactly what the weighting is doing. And that'll be more clear in a moment here.
Great.
Okay. I'm looking at my notes to make sure I'm not missing anything. Okay. And I promise this is the most math that we'll be doing in the whole course. Most of the other stuff is a lot more straightforward, but it's very handy to know these things. Okay, so first off, just remember that this for each loop right here is running over the points that are being currently looked up. They're the lookup points inside the radius of the currently infected point. So first of all, we need to find out what their infection value is. So we create a float called infection here and find out what that infect is on the current neighbor point. In the next line here, we're creating a vector. Well, we already have the vector, we've declared it, but we're taking this vector and saying we're subtracting the position of our current point from its neighbor. So let me draw here. So you can see these here. This point got infected. While it was still the neighbor, it's drawing a direction vector because we have vector 1 is